So now we've gotten into the second video. We're getting into market equilibrium, shocks to the equilibrium, whatever. If there are multiple equilibrium, we're going to call them equilibria, but we're not going to really deal with that until we get to game theory closer to the end of the week, end of the term. And so we've got a lot to kind of talk about here, right? So market equilibrium is a pretty fancy way of saying where do our two lines cross, right? So we've got this supply. Oops, let's go back to black. We've got these supply and demand curves. This point here where we cross is going to be our market equilibrium. And so our market equilibrium is achieved when all traders, so consumers and producers, can buy and sell as much as they want, right? In a situation in which no participant wants to change their behavior, is also an equilibrium, right? Everybody's content with where they're at. They can buy and sell as much as they want. They don't want to sell more. They don't want to sell less. They don't want to buy more. They don't want to buy less. Everybody is in content, right? At an equilibrium price P star, right? So whenever we have this combination, we are going to say that this is denoted, the equilibrium values are denoted with stars, right? It's just a fancy way of saying that these are the important prices and these are the important quantities. P star is that consumers want to buy the same quantity Q star that firms want to sell, and vice versa. At Q star, firms sell at the price that consumers want to buy, right? We also call this market clearing equilibria, which means that everybody in the market is going to walk away with everything that they need, right? Now, there's a couple things that happen here, right? Is that suppose we weren't at equilibria, right? Or like, let's suppose that one, right? So let's draw, instead of just supposing for right now, let's draw our two things, right? We are going to be, we've got our supply, we've got our demand, right? We've got our Q star, and we've got our P star, right? So now, suppose that we were above, right? So let's suppose that our price here, we were at P high, right? So we are cutting across here. We've got this associated quantity, these associated quantities. So what happens is that when P is greater than P star, quantity supplied, right? So this is where the quantity that we're at here exceeds the quantity demanded, right? And so when the quantity supplied exceeds the quantity demanded, it means that suppliers are going to have to try to lower their price in order to incentivize more people to buy more goods, right? This price is too high for a lot of people in the market, right? And so even though the sellers have a lot more like quantity that they need, really what they need to do is they just need to figure out a way to come back towards the center, right? So they want to move back towards here. And the best way to do so is just to lower their prices. And then that in the long term will reduce back to the equilibrium. Very similarly, suppose that this price was set too low, right? And now we've got these crossing points here. We're going to say the same thing, right? Is that our quantity demanded is far out exceeding the quantity supplied. And so people are willing to pay a lot of money for these goods. And so the sellers can raise their price and it will push us back up towards the equilibrium. So this is what we call the invisible hand, right? It was Adam Smith's big idea that markets will always kind of move towards the equilibrium. And it's because that there are these external, the way that consumers interact in the market with other firms and other producers is that people are going to be pushed back towards the equilibrium by themselves. Governments don't need to get involved. They don't need to start taxing. They don't need to do whatever. Excess demand and excess supply will be accounted for normally, right? We don't have to worry about much that come back to this. So that's it graphically. What if we wanted to show this like mathematically rather? So suppose that these were our two functions, right? Our quantity demanded and our quantity supplied. And again, you can tell that this is quantity demanded because price has a negative P, right? Right? I mean that our price is negative in the quantity demanded. Remember, the law of demand says that there has to be an inverse relationship between the two here. So if we solve this for P, right? We're just going to get QD minus 12. If we solve this for P, we're going to get 18 minus 2Q, or plus 2Q. 2Q minus 18, my fault. Right, and so we're going to have at quantity demanded equals 0, our price is going to be 12. And then we're going to have some sort of supply curve that comes up like this. Right, so this is going to be, and that'll be 12. Down here, this should also be 12. Yeah, I think we're good. I think we're good here. Cool. So yeah, so we've got these two. Now, to find our equilibrium, right? Let's say that we wanted to figure out what this Q star is and what this P star is. The best way to do it is just to set the two together, set the two equal to each other, right? Because where these two curves cross, the Q's are equal to each other and the P's are equal to each other. So if we set QD equal to QS, then we're going to get 12 minus P should equal 9 plus 0.5P, right? So let's subtract the 9 from both sides, add the P to both sides, divide, right? Then we are going to get, I think this is 2, right? So our P star should equal 2. Now, when we're trying to figure out what is the best way to get back to the quantity supplied, pick your favorite curve, right? Because they're equal to each other, both of them can back out the quantity supplied, right? And so let's just use QD because I think it's easiest because it doesn't have a coefficient in front of P. If we throw that P is equal to 2, oop, that's the answer. Minus 2 should equal 10. So our Q star here should equal 10, right? That's how you find the equilibrium. It's pretty easy, pretty straightforward. Not much is going to change from that. Again, this should all be pretty much review. But yeah, that's how you get to the equilibrium. So then what's the intuition, right? So again, I don't know why this is its own thing. I kind of screwed up on this slide. That's my fault, right? If we had these curves, right, at the equilibrium, quantities are going to be equal, right? So if this is Q, right, at this point, this is where QS is equal to QD is equal to Q star. Solving for anything can back out this price star, and then you can put it back in to figure out what your Q star is, right? Exactly what we did up here, right? We set them equal to each other because we noticed that they were equal to each other. We backed out this P star. We added this Q star to find Q star. Right, and again, this is equal to QS as well. So yeah, so that's the intuition. Let's do another example. So first, which one of these would be demand, right? I'll pause in real life for like another like 10 seconds. So this one is going to be demand because we're going to deal with this minus here, right? And this one is going to be supply because it has to be supply, right? So what are the equilibrium price and quantity, right? So let's set QD equal to QS. And this is going to give Q star. Well, this is going to give P star. Right, so we're going to get 110 minus 20p should equal 20 plus 10p. So we're going to get 90 should equal 30p, and p star should equal 3. And then from p star is equal to 3, we can then say that q star should equal 20 plus 10 times 3, or 50. Or alternatively, q star should equal 110 minus 20 times 3, which is also equal to 50, right? So you can solve it with either supply or demand, but you'll be fine either way. So I would just kind of keep going with this. If this makes sense, this is great. Like this is kind of the whole point of this chapter. It seems pretty straightforward, seems pretty simple. Let's do one last example. Let's do this in theory, right? So we've got A minus BP should equal C plus DP, right? We're going to add and subtract. And then we've got BP plus DP. So we've got A minus C over B plus D should equal P. And so this would be P star. And then our Q star should equal A minus B times A minus C over B plus D. Right? So it's in theory, it's fine, it's whatever. But if you can follow this, you can do whatever. You should be pretty good with everything. So now, suppose that we had some shocks, right? These shocks to these equilibria often occur from shocks to the external goods, right? The price of a complement, the price of a substitute, the income, whatever, right? We are going to call these shocks comparative statics, right? So comparative statics are going to be comparing static equilibrium, right? So imagine, coming back up here, we had this graph, right? Imagine that the shock to the supply curve that we talked about in the demand in the first video occurred. Notice that our equilibrium is going to shift up, right? And so when our equilibrium shifts up, we have a new equilibria, and that is going to affect both our equilibrium price and our equilibrium quantity because the place where they intersect is going to be at a different location. Okay. Again, we call these comparative statics. Shock occurs to one of the variables um, we hold constant, right? And we are going to call these exogenous shocks, which just means that they are not affected by us. So something external to our decision-making process happens. That's going to change the equilibrium, going to do whatever, and it's going to affect demand and supply. So what we're going to be comparing is static equilibriums, and these changes can be big or small, but it's easier to see if we do big changes. So we're going to do some bigger changes. So let's talk about some discrete shifts, what happens graphically, right? So what we should be able to do is graphically, and these are just going to be kind of qualitative directions. So suppose we had a demand, and then suppose we had supply, or sorry, that demand is not labeled correctly. This is supply, this is demand. Suppose our income increases, so our demand shifts out, right? So this is demand one, this is demand two. Well, we can see if this is price, P star, Q star, quantity. This increase in income that causes our demand curve to shift out, and remember, it shifts out because it's not a change to our variable of interest. We should be able to see that this, oops, that shouldn't be have been an eraser, that this price will increase to something new and something higher. And our Q will also increase as well. Right. So identifying the changes in price and quantity due to the change, if we had more graphical, like a more specific graph, we would be able to find these answers numerically, and we would be able to say that quantity would increase by X number of goods and price increased by Y dollars. But we should be okay regardless. Now, if we wanted to do this not graphically and we wanted to use some mathematics, then we would be able to also do this mathematically, right? So we have our quantity demanded, we have our quantity supplied, and we have our PC. So first, we need to figure out, so our PC changes from $3 to $6. So we know our quantity demanded is going to be the same, right? It's also going to be P. If we're not going to graph it, so we're not going to solve it for P, but just note our QS1, right? We know that this is going to be 9 plus 0.5 P, and our QS2 is going to be 8.4 plus 0.5 P. Right? So those are our two supply curves. Right? Now, if we solve for this equilibria like we normally did, so our original, this is going to be 12 minus P should equal 9 plus 0.5 P. And so this is going to be 3 should equal 1.5 P. And I think that we said here that P was equal to 2. Right? And then we plug this back in and we said that Q is equal to 10. Right? So now our shock, right? We're going to compare this 12 minus p still, but now we've got 8.4 plus 0.5p. And so instead of being 3, we're going to have 3.6, which should equal 1.5p. And so p star should be 2.4. And our q star should be 9.6. Right? And so if we came back up here, right? Let's say that these were our originals, right? Our price was equal to 2. Our quantity was equal to 10. Our new updated, oh shoot, this should go the wrong, I think this should go the wrong direction. Oh, it was a supply shift, so it should change them both. So here, let's update this to a supply shift instead of a demand shift. So if we changed this to a supply shift, so our supply increases, right? Then our demand can shift down to this 9.6, and our price is still allowed to increase to this 2.4, right? And so if we had the math behind these graphs, we would be able to note exactly what these changes were based on the graph, but the math will give the same result regardless. And so I'm always a big fan of the math because I think the math is a little bit more, I think it's easier to follow, but I don't think that you really need to worry about it either way. And so, yeah, this exact same thing here. We just did this. You can ignore that one. We did it all on this screen, so we should be good to go. So now let's think about small changes, or what happens if we have something that's non-linear, right? When we're thinking about stuff that happens non-linearly, we have to think about this in a little bit of a different manner. And this is where things start to get a little tricky and they start to get a little bit more confusing, one could say. And so this is where I guess the things that happen is that it just gets a little bit more theoretical, right? And so we're no longer dealing with just the numbers, we're dealing with kind of some more like implicit functions, right? So again, this you would read as quantity demand holding all other exogenous variables constant depends only on price. Okay, now let's say that our quantity supplied depends on price. And typically, remember, we said that it also depends on the price of the complements. Let's say that A is just some other component that plays in, right? We can call it a supply curve shifter, we can do whatever, but let's just call it the change, right? A is going to change, right? So we're still going to be the same. We're still going to do the same thing where we're going to find the equilibria by setting these together, setting these equal to each other, right? And so we're still going to set quantity demanded equal to quantity supplied. So quantity demanded is equal to quantity supplied. And so our equilibrium is still going to be found by setting these two equal to each other, okay? And so what we can do then is that when we see we've got some function here. So let's just say that this was p plus a, right? We would be able to write this as, or let's say 2p plus a. We would be able to write this as price is a function of the exogenous variable that we can't change, and everything that happens with this price is going to depend on this a, right? We would be able to, if we were given A, we would be able to know what P was. And in order to find P, we need to know what A is. And so we use this thing called the implicit function theorem, which you won't need, maybe you'll need to know the name, but you won't really need to know what it, really the math behind it just yet. But essentially it says that you can say that some endogenous variable or our choice variable is a function. So our choice variable is a function of our non-choice variable. And this is important. This is super important because when we say that it is not a function, like it's a function of our non-choice variable, it allows us to rewrite our equilibrium condition as this, which now, if given A, we can find P star and ultimately Q star. And so this is often what we use when we're thinking about very, very small changes, right? And so when we're thinking about small changes or nonlinear changes, when things might change a little bit, we're going to have to rely on the math and we're going to have to rely on our calculus, right? And this is why calculus is so important to this class, is because even in the first chapter, we're already using things that we wouldn't have been able to do in principles. So if given A, and I guess let's throw this in quotes so people aren't being like, given A what? We can find P star and ultimately Q star. And so what does this actually mean? Well, this means that A can impact our P star, right? Because we know this, right? And so if P star is given A, then we know that we can, and then ultimately we know that Q is a function of P star as well, right? And so Q should be a function of P star of A, right? And so ultimately A impacts both of these. And so given this, right, and this was here, let me just highlight this instead of trying to throw a box. Given this, we can use this to figure out how a small change in A, so a subtle increase in A, can change the equilibrium conditions by using the chain rule. And this is going to be interpreted in a lot of different ways. So this is going to be our change in demand from a change in price. And to understand the change in price, we need to have this change of price from a change in A, right? And so that's how you should be reading these, is we should be looking at this as this is our change in our demand for a given change in our price. And this is going to be how our price changes given a change in A, right? And so if we wanted to think about this as like kind of like some fake math, we would be able to cancel out these DPs and we would be able to see how demand changes following a change in A. Which is kind of crazy because A didn't even originally show up in our demand function, right? A only showed up in our supply function, but it still impacts these equilibrium demands and these equilibrium supplies. So for our demand influences, again, this is going to be our change in demand following a change in P and multiplied by our change in price from a change in A. Similarly, for our supply, we're going to have this partial change in S from a change in P. And the reason that we want to look at just the partial effect is because this will tell us what we're going to call the indirect effect. And this is our direct effect. Because we know supply directly changes from A, but we also know that because price changes by A, that supply is going to also have to adjust for the changes in price, much like demand did, right? So we're going to have the indirect effect, right? So if we wanted to draw this here as A and P, we know that both A and P influence supply, but we also know that A influences P. So in order to get everything here, we're going to have this direct effect and these indirect effects here, right? And so we should be able to figure out all of these to get the root cause of all of these. So the next thing that we would have to do, and the thing that we might be most important in, or most interested in, is exactly how to figure these out. And so I'm going to make this a little bit easier for everybody to follow. And we're just going to drop all of the parentheses. And notice that on the right-hand side, we do have the partials, but we're only going, the dPdA is a full. And so what we should do is we're going to subtract this to this side. And so we're going to get ddP minus the partial of S, partial of P, and this is multiplied by dPdA over the partial of S. Oh, that was a bad partial. Partial of A. And thus, dPdA should equal our partial of S over our partial of A over ddP minus the partial of S, partial of P. Right? And so if we want to think about this, and we want to think about like, what does this actually mean? Right? We're looking at this, it looks gross, looks whatever. Right? We should be able to figure out exactly what this means. And it says that this is the direct effect on supply over the indirect effects on demand and supply. And that should be the big difference in finding dPdA, right? And then solving for dQdA is just going to be the chain rule like we did beforehand. And so this chain rule should be pretty straightforward. We'll do whatever. So coming back up here, right? What do we know a little bit here? We know that dPdA is always negative. We know that dsdA, the partial, is going to be positive, right? We don't necessarily know how dsdA is going to look, but if dsdA is positive, then dPdA is also, or is negative, right? Because this is a negative minus a positive on the bottom. So this should be ultimately a negative. And if this is negative, then dPdA should be 0. So what this means is that regardless of the indirect effects, this change, the direction of the change, the marginal change in the price, following a change in some other thing in the supply, all depends on the effect that the direct thing has on the supply. So if we think about the price of the complement beforehand, right? I mean, of the input price, we said that if the price of milk goes up, the quantity demanded of lattes is going to go down, right? Because price, or this impact on price, is fully driven by the impact on supply, right? So our quantity supplied decreases, and so our price is also going to decrease. And that's pretty straightforward. That's pretty simple. It's exactly what the math says. We're going to do a couple examples with this, so don't worry much at all. So let's look at this example, right? So we've got quantity demanded should equal quantity supplied. So first, we say that P, if we wanted to write this to match above, is a function of this price, this input price here, right? And so if we wanted to figure out what dP dA would be, we would be able to do all sorts of things. So first, we should take a step back and we should find the equilibrium, or the equilibrium in theory, right? Because we have this quote unquote free floating variable here. We can't find an exact value, but we're going to be able to get 1.5p should equal, and this is where things are going to get a little weird because we're taking 9.6 minus 12. So I think this should be minus 2.4. And so and then if we divide everything by p, oh shoot, this should be a minus. We'll get positive 2.4 over 1.5 plus 0.2 over 1.5. Then we can say that dPc should equal like 0.133. And so what this means is that if the price of the complement increases by $1, our price of our own good should increase by like 13 cents or something like that, right? So if PC increased by $1, then P should increase by 13 cents. Okay. Now, if we wanted to think about this the other way, right, to figure out quantity demanded, we know this is true. And so dq dpc, right, because we know this is here, dq dpc should equal, and this is just pulled from above, replace the PC's with A, and you'll be able to find it, right? But this derivative with respect to P was -1. And then we know that dP dPC was 0.133. And so dQ dPC should equal -0.133. And so this is what we would call a comparative static. The price of the complement increased by $1, then our price of the good increased by 13 cents, and our quantity demanded decreased by, let's say, 1.3 million tons or something, because we're a big producer, right? That is a comparative static. If you understood how to get to this point and how to follow along, you are doing incredible. We can do another example here, right? So let's set the Q's, let's set these equal to each other. And because I changed this to an R just in case people got confused with the PCs, I'm going to move everything to this side this time. So we're going to get 260 plus 20R should equal 3P. So dP dr, and then I guess we should divide again. Should equal 20/3. And then we have Q, which should equal 300 minus P of R. And so dQ dr should equal dQ dP, dP dr, which should equal -1 times 20/3, or dQ dr should equal -20/3. And again, you could do that for QS if you wanted to, but it's just easier to do it, in my opinion, with with the quantity demanded, because it's only one term, right? You would definitely have to control for this extra effect here, but it would be fine. And so, yeah, that is essentially the elasticities. Well, that will take us to the elasticities.